In this video, we're going to learn the relationship between chemical potentials and work. Alright, so far in this unit, we have defined the chemical potential simply as the molar Gibbs energy of a component in a mixture. Okay, but it turns out that that chemical potential actually is also related to work, and we're going to see how in just a little bit. Alright, before we get started, I think it's a good idea to try to recover here the dependence of the Gibbs energy on variables. Alright, so from our work or with pure substances, we know that the variation of the Gibbs energy with pressure and temperature is provided by this expression. And again, this is something that we derive for pure substances. Alright, so this is when we're looking at pure water or pure ethanol or CO2, whatever it is. And then the only thing that could change was just simply pressure and temperature. But of course, we have started to look at mixtures, and those are thermodynamic systems in which concentration might also vary, right? So the way that we actually have defined the Gibbs energy when the concentration is at play, we've said, well, this is simply the chemical potential of species A times the number of moles of species A, and then the pertinent values for component B. That's if you have a binary mixture with only two components. Obviously, this can be extrapolated to multi-component mixtures. Notice that we can group together all of these terms simply in all these terms into an expression that is just a sum, right, of the chemical potential of all of the components multiplied by the number of moles. But what this suggests is that there is going to be a dependence of the Gibbs energy on the composition, right? If you change the composition, that is the number of moles of A and B or I, then the Gibbs energy ought to change, right? And that expression is going to be like this: chemical potentials of I, and then the change in the moles of I. That's how the composition changes, right? So this is what happens for mixtures when we have them at constant pressure and constant temperature, right? So you can clearly see that there's going to be a global dependence of the Gibbs energy and variables that incorporates the dependence on pressure and temperature, and also the dependence on composition if you don't have pure substances. And we can write that here. So the variation of the Gibbs energy with all variables would be this one, minus SDT, and now we also incorporate the term for potential variations in composition, which directly depends on the chemical potential. Alright, great. So that has been a nice point of view of the Gibbs energy, again, going from pure substances to mixtures where you have that there's dependence on composition as well. Alright, so now the question is, how is this related to work? Well, something that we saw in the last unit was that there is a relationship between the change in Gibbs energy in a process and the maximum non-expansion work that you can extract from this process. Okay, so that prime means non-expansion. Alright, in differential form, this is simply going to be equal to the following. Well, very good, but it turns out that now we actually have a dependence or a way to express the variation of the Gibbs energy in the conditions, and that is actually going to come in right here. All right, so again, this would be exactly identical to your differential of maximum non-expansion work. All right, so that's fine, but let's suppose now that we're working under conditions of constant temperature and constant pressure. And actually, those are conditions that we normally work under all the time, right? So at constant pressure and constant temperature, these terms cancel out, and we find a very simple and nice dependence of the Gibbs energy, of the maximum non-expansion work on composition or chemical potentials. Right, so there you have it. What this tells you is that if you have a mixture with some change in which the composition is changing, you actually can extract work from that. Right, so that might sound a little exotic, but it really isn't. think about a chemical reaction in which you have reagents moving towards products, right? What we know is that we can, if this is a combustion reaction, for example, we actually know that that variation of reagents into products, that can be used to extract work, okay? For example, if this is glucose and you're metabolizing that in your cells, then what happens is that you can extract the energy stored in that glucose to do any type of non-expansion work, such as jumping against gravity, or perhaps contracting muscles, or maybe pushing ions against gradients in your brain, right? So that's exactly what this is telling you, the relationship between that non-expansion work and the variation in that composition that is taking place in chemical reactions. But this also applies to situations in which you might not have a chemical reaction. For example, you might remember from your general chemistry courses, the units in electrochemistry, that there were some systems called concentration cells, and those were very simple, right? You just had the anode and the cathode, and here you would have a solution of the same ions. So suppose that this was simply silver, and here you have silver plus, and then the other electrode is the same, it's a silver electrode. You also have here silver plus, right? Here, you could actually measure a voltage if the concentration was different, right? If you had here 0.1 molar and here 1.0 molar, simply this difference in concentration allows you to actually measure a voltage, right? And that is ultimately connected to this, right? That electrical work that you can extract from this concentration cell is exactly this. The only thing that is different is actually this difference in concentration that you had in these concentration cells, right? So this is kind of a nice reminder of how this explanation of chemical potentials, this concept of chemical potentials and its relationship to work, really ties in very nicely with things that we have studied when we're looking at the metabolism of glucose, all the way to other systems such as concentration cells in electrochemistry. All right, in the next video we're going to continue to see how this most important concept in thermodynamics, this chemical potential, how we can write that as a function of concentration, but we're going to be moving from gases all the way to solutions.